everyone. I am Nazia, and along with Firi, Anna, and Omar, I'll be presenting the paper on efficient language models with attention sinks. Let's go to the introduction, please. Next slide, please. So next, please. So we'll be introducing LLMs. As we all know, large language models are the AI algorithms that use deep learning techniques to produce data and to process data to understand, summarize, generate, and predict new content. But the issue with using large language models is that they have a limited length extrapolation ability. That is, their performance degrades when the sequence of the length it goes beyond a predetermined data. For example, if the data has been pre-trained on 4,000 tokens, anything that goes beyond it reduces the efficiency of the language model. Next slide. So to solve this problem, there is a window attention technique, which maintains only a small size of window or a fixed size, not really small, but a fixed size of window, which slides. It helps reduce the memory usage, and it has a constant memory usage and decoding speed. But the problem is, again, the same, that whenever the sequence length exceeds the cache size, the model collapses. Next slide. So a solution for this is recomputation at every window level, where as the window slides and uses a new token or adds a new token, the value is recomputed. But this is very computationally expensive, obviously, because computation at uh, computation of quadratic attention within the window is very expensive computationally. It makes the computation slow. Next slide. As we see from these autoregressive LLMs, that a large amount of attention is being paid to the initial tokens. If you look at the pictures in this slide, you see a red strip in every layer. This is where the main attention is being paid by all the tokens. These are initial actually 4 tokens, and despite whatever semantics is there in the sentence or in the text, the initial 4 tokens, they are being paid the most attention. And these are termed as attention sinks in this paper. Next slide, please. And as you can see from this example of Llama 213B, that these the initial 4 tokens, when they are taken as attention sink, considered as attention sink, the perplexity of the model is very low. And even if the initial 4 tokens are simply replaced by a new line symbol, even then the perplexity is almost the same as in when there is a numeric syntactical token, which means that whatever be the semantics of the paper of the input, the initial 4 token will be given the most attention. Next slide, please. Keeping this in mind, the authors of this paper propose a streaming LLM. As you can see, the yellow strip in the graph, they keep this constant. These 4 tokens will always be used in computing the output, whereas other tokens will keep on changing as the window slides. For example, if the window of the token is between 6 and 9, even then 0 to 3, the first 4 tokens will be there, and the next tokens that will be used will be 6 to 9. When the window slides over to the token in the next to the next token, it can be from 7 to 10, but initial 4 tokens 0 to 3 will always be used for computation. Now, the authors use this idea and they want to predict that if this streaming LLM can be used for infinite length of inputs without sacrificing the efficiency of the performance. Next slide. Phoebe, over to you.
Okay, thanks, Nazia. Here I'm going to present about the works related to this research paper. And so researchers have mainly focused on 3 areas, which is making LLMs work with longer texts, called length extrapolation, and context window extension, which is basically trying to allow them to understand more words at once, and also improving LLMs utilization of long text. So let me start with the first one. LLMs, which is like length extrapolation. So the goal is to train them on shorter text, but still have them understand longer ones. And one approach which uses relative position encoding was tested in the ROPE, or Rotary Position Embeddings Research Initiative, that transforms queries and keys in attention layers for relative position integration. So this helps LLMs understand the position of words in a sentence. However, this method doesn't work well when the text is much longer than the model was trained on. So when we move to the second area, which is context window extension, this helps them process larger portions of text in a single step. To do this, they try to improve the efficiency of training and reduce the memory needed. But even with these methods, LLMs still struggle to handle long texts. And the final research area that I'm going to discuss here is improving LLMs utilization of long text. This involves using LLMs to make the best use of the information in those long texts. But this is still a challenge, and more work is needed to achieve this effectively. Can you move to the next slide? And next slide. Okay. Next. Okay. So window attention techniques fell, and the concept of the attention sink explains it. The window attention technique, which limits what models pay attention to, doesn't really work well for long texts. This is because the model focuses too much, LLMs focus too much on the beginning of the text and ignore important information elsewhere. And this results in a surge in perplexity when excluding initial tokens, which means perplexity goes up and the model has a harder time predicting what comes next. Model consistency focuses on initial tokens, and the model tends to keep looking at the start of the text, even in different layers and parts of its attention mechanism. So when we remove the connection of the first words with other words, meaning removing the initial tokens key value pairs, or KB pairs, it messes up how the model pays attention and makes it perform worse. And when we replace the first words with line break symbols, the model gets more confused and its perplexity increases. The initial words are important for the model to understand the text well. Actually, replacing them with line break symbols is better than removing them. Still, the perplexity is relatively constant and stable. However, if we put the initial words back, the model starts to perform better again, and its perplexity improves. And usually adding 4 initial words back into the text is enough to make tokens back into the text is enough to make the model work well and have good perplexity. Thank you.
Oh my. Okay, so sorry. We've been talking about attention and perplexity a lot. Let's first find out or understand these terms better. So attention is when when a model is generating the next word, or here we say token, from the context. The model will pay more attention to certain words that are more helpful instead of having to look at every single word. So for example, if the context is the musicians sat together and played, the model would just pay attention to musicians and played a bit more, so that instead of predicting like played helicopters or played chess, it would know that it would want to predict something like played songs or played instruments as the next word or token. And so when we were talking about the different attention designs, dense attention would be where the entire context is everything that has been inputted is considered. So in this example, it will be the whole sentence, the musicians sat together and played, etc., etc. And so this blue part would be this context, and this red part will be the current token that is being predicted. Whereas in window attention, because as inputs get really, really long, the model would only consider the last few tokens. So for example, it might just consider last 3 tokens. Obviously in real world examples, this might be like 3,000 tokens. And so it would just look at together and played and have to predict the next words. So the test that the authors used to compare the different models was the PG-19 test developed by Ray et al. In 2019. It's named after Project Gutenberg, which is a dataset of free online books. And they used 11 gigabytes of text in total. So for training, they trained the models on 28,000 books. For testing, they trained all of the models they tested them all on 100 books. And these were all continuously inputted because these are streaming models. And they use the test metric of perplexity. Now, we've been talking about perplexity a lot. For those who aren't as familiar with natural language processing, this is how it's calculated. It's 2 to the power of entropy, where entropy is basically the average of the average log likelihood. And none of this really matters. We just need to pay attention to this probability here. The probability of the ith word given the previous words from 1 to I minus 1. And so what are these probabilities? So for example, if we're predicting word 1 or the first token, what word is more likely to start a sentence? If we have a very limited vocabulary of just these words, then a or the has a high probability of starting the sentence, whereas a full stop has no probability of starting a sentence. And so the model would choose because this has the largest possible probability, and then it would record this part as 0.4 and add them together across different i's. So for example, if we're in the middle of the sentence now and we already are given and red as the first 2 words, and the model is predicting the third word, because the first 2 words are and red, there's a higher likelihood that this would be fox rather than dog, because dogs aren't usually red. And so the model would choose fox and record this probability as 0.55. And so the model is more sure that the third word is fox than it is sure that the first word is And so here, this would have a better perplexity score, and this would have a worse perplexity score. So if none of this made sense, all you need to remember is that if perplexity is, say, 1,000, that means that the model's level of perplexity or its level of confusion is like having to choose one word from 1,000 words. So that's bad because there's a lot of options. Whereas if perplexity is low, like 5, then it's like the model is choosing one word from 5 words. So it's very confident in the word that it did choose. And a little more examples. So for example, grammatically incorrect sentences would have higher perplexity versus grammatically correct sentences like this. And then sentences that are gibberish would have higher perplexity compared to sentences that are more reasonable. And so in the PG-19 test, there was context provided. So here, for example, if the context was, we met in a dream, I say, we were falling off a bridge, then this sentence, she fixed the GPU, like these words would all have higher perplexity because it's not related to the context. Whereas this sentence, she looks at me, her eyes widening in recognition, would have a lower perplexity because it's related to the context. Okay, now let's get into the meat of it. So the authors first suggested adding attention sinks to pre-trained LLMs, as my colleagues have mentioned. Oh, great. This is a demo where on the left, without streaming LLM, the model performance breaks, whereas on the right, the model is able to continuously stream. Okay. Oh. Okay. So yeah, for the different models, these are all without streaming LLM. This is log perplexity. And so as the input length increases, we can see that the perplexity suddenly skyrockets when the cache size is exceeded, which means that the initial tokens were removed. So across all the different models that they tried, StreamingLLM performed the best with the lowest perplexity, whereas window attention, which is what we really care about, its perplexity would increase after this cache size is exceeded. So why does perplexity explode once the initial tokens are removed? Well, this comes from the attention mechanism that uses the softmax function. So the softmax function forces all attention scores to sum to 1. And so after calculating the attention scores for the existing tokens, all the extra attention for it to sum to 1 needs an outlet. And since initial tokens are essentially global tokens that all other tokens have to take into account for output, like the initial tokens are always there for all the tokens after it. Because they're always there, these initial tokens tend to collect all of this extra attention for the softmax function. And then in sliding window attention, when the initial tokens are removed from the cache context because the window has slided away from the first tokens, then the model suddenly has to redistribute a large amount of the attention scores. And so perplexity would explode. So to solve this issue, the authors designed StreamingLLM. So they looked at the existing methods for attention. They rejected dense attention because the large memory requirements, you have to remember, the model has to cache or store all of the information from all of its inputs. And that's just unrealistic with our current memory, like technology in memory. And they also rejected the sliding window with recomputation because every time these new caches are recomputed to kind of summarize information from the past, this process takes L squared time complexity, which just is unfeasible as outputs are increased, as inputs, lengthen. And so they chose window attention, which has reasonable time complexity. But the thing is, right now, when these initial tokens are removed, the model performance breaks. As you can see, it's outputting complete gibberish. And so they added attention sinks here, where whilst keeping this window of cache or information, they would also keep the initial tokens. And these gray tokens will be removed as we start predicting further and further inputs down the line. Another question the authors came across was, could this whole problem not be related to attention sinks? Could it be just because of poorly designed positional embeddings, which tell the model where which word was? And their answer was no, because all of their vanilla pre-trained models that they use, like Pythia, Falcon, etc., they all tested these with rope or alibi, which rotary positional embeddings, or attention, what was it? With linear biases, I think. Sorry. So these are the most modern positional embeddings that they use, and they still had perplexity increase. And when they incorporated these positional embeddings with StreamingLLM, these models perform better. And so this is a constant that didn't change anything about perplexity, or it didn't change the issue that we're trying to solve. So the structure of StreamingLLM is that first you take a pre-trained model, for example, like Llama 2, 7 million parameters, or MPT, and then we would use the sliding window mechanism. And then here, first we would re-index the positions of the tokens to remove gaps. So because we're using sliding window, we're removing these gray tokens. But then instead of, so say we're predicting the 9th token. So our current cache tokens are 0, 1, 2, 3, 4, 0, 1, 2, 3, 6, 7, 8, 9. But then instead of saying 0, 1, 2, 3, 6, 7, 8, the token positions that we would tell the model would be 0, 1, 2, 3, 4, 5, 6. So this gap here is removed. And this has just been proven to improve like long range dependencies. And then we would apply either rotational position embeddings or alibi positional embedding to the model, and then keep the initial 4 tokens as attention sinks, these 4. Okay, so since we found this mechanism that works, the authors asked, could we just train these LLMs with an attention sink to begin with? So, so they tested this. First, they used vanilla models, as we've already been doing, these pre-trained models with using normal, the softmax function. And then recognizing that the issue stems from softmax, they tried using models with softmax off by 1, which Evan Miller just suggested earlier this year, where we would add 1 to the denominator of the softmax function. And because 1 is e to the power 0, it's essentially the same as adding a token with all 0 features. And so that's why they call this a zero sync model. And then lastly, they tried using what they call a learnable sync model, where they train the model with 1 attention sync. And the experiment results were as follows. For the vanilla model, when they tested it, they would have to add 2 tokens before perplexity went back down to 18. For the zero sync, they would have to add 4 attention sinks before the perplexity went back down to 18. And for the learnable sync model with 1 attention sync trained, in testing, they would only need to add 1 attention sync for perplexity to go down to 18.01. And this performance is even marginally better than this, depending on whether you think variance in like the experimental procedure was the cause, or if the learnable sync is actually better. So either way, 1 attention sync was already enough, which is great. And so this is a more graphical representation of basically what we saw, which is this is log perplexity, and as input length increases, perplexity remains pretty stable, around 1.1 to 2. Same for Falcon, same for they tried other models that I'm not including here. And if we compare this to the models without StreamingLLM, as we can see, when input length is at 20K, the model of perplexity is already at 8. Whereas here, it's up to 4 million, and the perplexity remains constant around here. Even the best performing model, which is Falcon, had perplexity of around around 2 with StreamingLLM, when before it was around 2.5 here. And so there's an objective improvement in model performance with StreamingLLM.
So, hello guys. Okay. As the author claims at first that they can improve the streaming LLMs by introducing the attention sync. To state this claim, they trained both models, one with attention sync and one without attention sync. They actually trained each model with 160 million parameters. To set up the experiment settings, we will show in the next slide. Next, please. Okay. They used the Pythia framework. This framework has many models. They specifically choose one with 160 60 million parameters and trained the model on NVIDIA GPU server 8 by A6000 server, which is designed for the high computational models. The settings of each model is the same as the code base for Pythia 1600 million. They use the same learning schedules, same initializations, and so on. And both models, the one with attention sync and one without attention sync, both are trained for 143,000 steps. So the next slide. Okay, to wrap up the paper suggested an introduction to a new mechanism, which is attention sync, that improved the streaming LLMs without sacrificing the performance. They trained the two language models who stayed their proof. They used the same settings for the Pythia 1600 million model. They used the pile dataset after deduplication. Both the models are trained on 143,000 steps, and as the final, they stated their proof that attention sync could improve the streaming LLMs without sacrificing the performance or affect the efficiency. And that is ready for any questions. Next slide. Do any one of you have questions? Okay, I think that is